So, welcome again to the new lecture of this course, Fundamentals and Applications of Dielectric Ceramics. So, let us just briefly recap what we did in the last lecture. So, in the last lecture we discussed the details of dipolar polarization, we looked at the whole analysis which is called as dipolar relaxation, and what we saw was that dielectric constant through the whole analysis worked out as epsilon r prime is equal to epsilon r prime infinity plus epsilon r s prime minus epsilon r infinity prime divided by 1 over omega square tau square, and epsilon r double prime was equal to omega tau divided by 1 plus omega square tau square into epsilon rs prime minus epsilon r infinity prime. So, epsilon rs prime is called as basically the static dielectric constant, and epsilon r infinity is called as high frequency dielectric constant, and you can see that there is a dependence on frequency here. So, these are called as Debye equations as we saw, and when you plot them together, then epsilon r prime, it goes from a value epsilon rs prime, undergoes a relaxation before it converts into. So, this is epsilon rs prime, this is epsilon r infinity prime, and this relaxation happens at a frequency, specific frequency, which is for which we say. So, it is better to plot omega tau, because you can say that this happens at omega tau is equal to 1, okay, and this is where your and the epsilon r double prime undergoes a maxima at this point, and this is okay. So, this is what the behavior is, and tan delta can be obtained from this as epsilon r double prime to epsilon r prime. So, when you plot, now this process is temperature dependent because the relaxation time is a temperature dependent entity. So, when you make for example, when you look at the variation of tan delta as a function of temperature, tan delta, the tan delta, and you plot the frequency, let us say at lower temperature this is the frequency, at higher temperature it tends to show a rightward shift. So, this is how it will vary. So, this will be basically increasing temperature. So, the relaxation will occur at certain frequency. So, this is omega 1. So, we can write it as omega 2, omega 3, and the frequency will shift to right, because as we increase the temperature, the diffusion becomes faster. As a result, the relaxation times slows down, one goes to relaxation time decreases as you and the frequency, you can do the relaxation at a faster frequency. So, this is generally the trend that you observe, that the tan delta peak shifts to higher frequency as you increase the temperature, and as a result there is a strong temperature dependence. So, when you plot, you can also plot the, for example, this maxima at which tan delta occurs. So, let us say you plot log omega max as a function of. So, this has a Arrhenius kind of behavior. One can determine the activation energy from these plots. The maxima of these plots as a function of temperature will give you a behavior which is basically omega is equal to omega naught exponential minus qa by kt. So, essentially one can determine what is the activation energy of migration or dipole relaxation as a function of temperature when you do temperature dependent measurement of dielectric properties. So, this is a very useful. So, when temperature dependent measurements of dielectric materials are very useful way to understand the intricacies of dielectric materials, the activation energy, what kind of defects you might have, because activation energies are something which are, these activation energies are signature of what kind of defects and processes are present in the materials. So, one can make very nice conclusions about what happens in various different kinds of materials. So, now what we look at is we look at little bit more details of how do you characterize dielectric materials. So, for characterization of dielectric materials, we need to define dielectric materials in a little bit electrical form. So, basically what we are going to look at from the characterization perspective now, how do you represent a dielectric material in a circuit form? So, dielectric material basically electrical circuit representation. So, here because when you do characterization of dielectrics, often you need to model the dielectric properties, and when you do modeling of dielectrics, the modeling requires the material to be represented in the form of electrical circuit. So, ideal dielectric material will have only capacitive contribution, but in a real life dielectric is hardly 100% capacitive. As a result, it tends to have resistances in it. So, how do you model those capacitors and resistances for a dielectric? So, let us say a perfect dielectric. First take example of perfect dielectric. The perfect dielectric is basically modeled by an equivalent RC circuit. So, basically you have a capacitance C1 which is in parallel to a capacitance C2. So, this is a capacitance C1, this is C2, and this is in series with a resistance, let us say R2. Okay, so this is an equivalent RC parallel circuit, which is as it is called as. So, let us consider the first admittance of this admittance is represented by Y. Admittance is basically, you can say, Z prime, which is inverse of impedance. So, one can write Y is equal to 1 over Z, and this will be 1 over Z1 plus 1 over Z2. Okay. And why this circuit has been chosen, it will also become a little clear as we go on. Okay. So, it is not all that coincidental, it is not all that fluke, there is a logic to it. So, we will see that in a little while. So, this Y is 1 over Z1 plus 1 over Z2, and what is Z1? Z1 is for this one. So, here you only have a capacitance C1. So, this will become 1 over I omega C1. And what is Z2? Z2 will be 1 over I omega C2 plus R2, right. So, admittance can be written as I omega C1 plus 1 over R2 plus 1 over I omega C2. All right. Now, considering in electrical circuit, wherever you have resistances and capacitances, the product of RC is taken as time constant. So, in this case, let us say R2 C2 is equal to tau 2, which is time constant. So, again we can express the admittance as Y can be I omega C1 plus C2 divided by tau 2 plus 1 over I omega. Okay. So, here let us see what we have done. Yeah. So, we have taken C here. So, this we have made this as C2 R2, removed C from here, and we have taken C on top. Okay. So, this will become like this. Alternatively, we can write this as omega square tau 2 C2 plus 1 over omega square tau 2 square plus I omega into C1 plus C2 divided by 1 plus omega square tau 2 square. So, if you simplify this, you will get this expression, that is omega square tau 2 C2 divided by 1 plus omega square tau 2 square and plus I omega into C1 plus C2 divided by 1 plus omega square tau square. Now you relate this to dielectric constant. So what is this? Admittance is equal to 1 over Z, and this is related to dielectric constant as epsilon double prime plus I epsilon prime into omega C naught divided by epsilon naught. This is the that we did last time, the frequency dependence of dielectrics, and this is basically nothing but epsilon r double prime plus I epsilon r prime into omega C naught. You can express this in another form. You can, if you multiply this by I, so this will become minus I omega C naught into epsilon r prime minus I epsilon r double prime, and this is what is basically epsilon r star, right, the complex form of dielectric constant. So we can express this in this form. So y can be represented as epsilon r double prime plus I epsilon r prime into omega C naught. Now if you compare this with our the equation that is shown in the previous page, previous line. So this y and this y you compare, just match the real and imaginary part, and you will get the values of static and the real and imaginary dielectric constants. So what we will get is, for epsilon r prime we will get C1 divided by C naught plus C2 divided by C naught into 1 over 1 plus omega square tau 2 square, and epsilon r prime double prime will be C2 divided by C naught into omega tau 2 divided by 1 plus omega square tau 2 square. Now this is very similar to what we saw earlier. Earlier we said that omega epsilon r prime is equal to epsilon r infinity prime plus delta epsilon, which is basically static minus infinity, low frequency minus high frequency, divided by 1 plus omega square tau square. So if you imagine this equation, if you remember this equation and compare this with, so basically C1 by C naught is nothing but your C1 by C naught is nothing but epsilon r infinity prime, okay, and C2 is the difference between the two, the epsilon r s prime minus epsilon r infinity prime. So that is what this equation is. So basically your C2 has turned out to be epsilon s minus epsilon infinity into C naught, and C1 is nothing but epsilon infinity. So C1 represents the high frequency dielectric constant and C2 represents the difference between static and high frequency, and that is why this circuit is not a fluke, because this circuit gives rise to exactly the same equations that we derived using Debye equations. So this is the equivalent RC circuit model for a perfect dielectric, which means which follows the Debye behavior. What happens when we do not follow the Debye behavior? Then there is a deviation. So when you do not follow Debye behavior, then what happens is that your relaxation times, you do not have a unique relaxation time, you have multiple relaxation time. So as a result, this equation gets modified as, the Debye equations get modified as epsilon r infinity, epsilon r star minus epsilon r infinity prime divided by epsilon rs prime minus epsilon r infinity prime, and this is equal to 1 over 1 plus I omega t to the power 1 minus alpha. So this is modified equation, and this was done by gentleman called as Cole. Okay. So here instead of, so here alpha is a parameter whose value will determine whether it is an ideal or not ideal parameter. So alpha is equal to 0 will mean your system is ideal Debye system. And deviation from alpha would mean that your system is, so alpha greater than 0 would mean your system is non-ideal in nature. And what it means is that basically alpha represents the distribution of relaxation times in the material, and what it means is that you have different defects responding to different frequencies. As a result, you have multiple relaxation times. So, distribution of relaxation times. So, if you plot now, for example, epsilon r double prime versus epsilon r prime, you should ideally get a semicircle like this, and the frequency goes in this direction. So, this is for a ideal dielectric, but in reality you will see that your semicircles are hardly obtained. You obtain suppressed semicircles or raised semicircles, which means you have some values of alpha, which means material does not have a single relaxation time or single entity, single dipole, rather it has multiple defects which respond differently to different frequencies, as a result causing a variation in alpha. So, now let us build upon this semicircle. What is the use of this semicircle? Well, the use of this semicircle lies in what we call as technique called as impedance spectroscopy. So, impedance spectroscopy is a technique which is used to impedance spectroscopy is a technique which is used to characterize dielectric materials. So, you saw that admittance is related to electric constant. As a result, the impedance is also related to dielectric constant, right. So, impedance and admittances are related to dielectric constant. So, when you measure impedance, you should also, when the dielectric constants plot show the semicircles, you should also get the similar semicircles in the plot of impedances, and impedances are measured on equipments called as LCR meters or impedance analyzers. And there are various companies which make them. So, I am not going to advertise for any particular company, but so these are the equipments which are used for varying. So, essentially you can say that intercepts of, if you take the intercept of semicircle as we saw last on x axis, that would be basically, so we saw that epsilon r prime double prime and epsilon r prime shows a semicircle, right, like this. The intercepts are basically, so this is you can say, and the frequency varies like this. So, this is low frequency intercept. So, this is epsilon r infinity and this is epsilon r s. So, the low frequency, so this is prime, let us say in this case real part. So, the low frequency intercept is epsilon r s r infinity, and the high, sorry, this should be s not r, this is low frequency, this is other way around. So, the low frequency should be the static dielectric constant and the high frequency intercept of an ideal semicircle should be the high frequency dielectric constant, and the maxima of semicircle will occur at omega tau equal to 1, or you can say omega r c is equal to 1, in this case r2 c2, but and this should follow the semicircle equation. So, the semicircle equation would be, and these plots are also called as, they are called by different names, Kolkol plots or Nyquist plots and so on and so forth. So, the equation of semicircle would be epsilon r prime omega minus half of epsilon r s prime plus epsilon r infinity prime to square plus okay, this is the equation of semicircle. So, if you Google, let us say what is equation of semicircle, you will find similar form of equation semicircle. So, you will have So, if you take different values like y minus something square is equal to something else square plus 1 over another factor square. So, this is the equation of semicircle, which is basically obtained by removing omega tau from the equations that we have derived earlier. So, we derived the equations for let us see which equations were these. Yeah, so we derived the equations for dielectric constants. So, essentially we derived equations for epsilon r prime and epsilon r double prime. If you remove omega tau from these equations, remove omega tau, if you remove omega tau, this is what you should get. Okay. The variation of dielectric constant. So, this is as a function of frequency, right. We had the equation. So, if you remove omega tau, this is what you should get, which is the equation of a semicircle. So, let us do a little bit more with this, and before we, so when you plot epsilon r prime versus epsilon r double prime to prime, let us say we get this semicircle. Okay. So, the semicircle essentially the frequency increase is shown in the inverse direction from right to left, and let us say if you want to measure at this point. So, the dielectric constant will be, so this would be epsilon r star, and net dielectric constant. So, within this you will have this as x and this as y. Okay. And now using these x's and y's you can write the equation of semicircle, right. And here this would be epsilon r infinity, this would be epsilon r s, and this is basically nothing but C1 divided by C naught, and this is nothing but C1 plus C2 divided by C naught. Okay. So, a perfect dielectric, so this would be the case for a perfect dielectric, where you can calculate x's and y's and you can find out at this point this will be omega tau is equal to 1. So, x's and y's and the difference between this. So, essentially you will have x square plus y square is equal to this square, right. So, this will be a 90-degree angle, right. For a perfect semicircle this would be 90-degree. As a result, x square plus y square would be square of epsilon r s prime minus epsilon r infinity prime. Okay. So, this would be the, you can see x square plus y square is equal to epsilon r s prime minus epsilon r infinity prime square, and if you look at the previous equation, this is what you have. This is, you can say, some sort of x square, this is y square, the 4 will go of course on the other side, this is what it is, right. So, what you should obtain for a perfect dielectric is like this, a semicircle, but for a real dielectric often what you see is that you have these sort of upturns like these, and these are, when you see these upturns, basically you have high losses in the material. Material is lossy, it has defects, it has other things which give rise to these kind of losses, and this is something that is a problem. Okay. And so, when you model this now, but in a real material you hardly see one semicircle. In a real material the situation can be a little bit more complex. You might have a situation in which, so you plot epsilon r double prime to epsilon r prime, and you might have situation like, so you will have one semicircle, you will have another semicircle which is sort of overlapping this, you may have another, so it could be something like that, then you may have another semicircle which is overlapping this. So, eventually you will obtain a plot which will look more like this. Something like this, and this is what you have to model. You have 3 semicircles here, and these may not be perfect semicircles. Okay. So, may not be perfect semicircles. So, you need to make appropriate models for them. For example, let us say if you have in a system, polycrystalline system, you have a grain contribution, you have grain boundary contribution, and then you have some other interfaces, right, like electrode interfaces and things like that. So, grains generally respond at higher frequencies, grain boundaries require at little lower frequencies, and this is increase in omega, and interfaces will respond at another frequency. So, it is possible that you have one impedance for this system, another impedance for this system, another impedance for this system, and then you also have to take care of contact resistances in the system RC, and this Z may be, it is like this, or it could be series of something like this. There are various possible circuits which are possible depending upon the nature of defects. So, as a result, this is far more complicated. So, what generally we do as a scientist is that we measure in the impedance spectroscopy, we first measure impedances, okay, convert these impedances. So, from these impedances we make plots of real. So, similarly when you make a plot of Z double prime to Z prime, you should also get these semicircle like, so you should have these kind of semicircles as we saw earlier, and we make plots of Z double prime versus frequency, Z prime versus frequency to determine the transition, to determine where the maxima is occurring, how they are behaving and things like that. Then you make these plots. From these plots you determine what is the resistive contribution. So, you separate out the resistive and capacitive contributions. From these different semicircles you find out for different components so if you have, let us say, two semicircles, you will have for one R1 C1 and for another one you will have R2 C2 and so on and so forth. So, you differentiate between different relaxation times, different resistances, and then you also make temperature dependent measurements. To distinguish clearly between the grain and grain boundary contributions, for example, the activation energy for grain will be different, the activation energy for the grain boundaries will be different. So, as a result, when you plot the relaxation times as a function of frequency or temperature, there is a possibility in some cases you will have distinct behaviors. So, at high temperature you may have this activation energy, at low temperature you may have this activation energy, and these will correspond to different entities. One may correspond to grain, another may correspond to grain boundaries, and so on and so forth. So, doing temperature dependent, and then of course, not only you can make Z prime versus Z double prime versus Z prime, or Z double prime versus frequency, or Z prime versus frequency plots, you can also calculate a quantity called as electrical modulus. Electrical modulus is called as M, which is related to Z, okay, and then using electrical. So, the problem with Z double prime is that high frequency contribution in the impedance spectra. When you plot Z double prime versus Z, often you will see that high frequency contributions are little subdued, but when you make measurements of M double prime versus M prime, the high frequency contributions are more explicit than the low frequency contribution, and this is because of the correlation between the two properties. So, you measure impedance, you analyze electrical modulus from impedance, do a temperature dependent analysis and find out the contribution from entities such as grains, grain boundaries, and find out difference between the two. So, impedance spectroscopy is a very powerful technique to analyze materials. Unfortunately, it is not the focus of the course, but there are several papers. For example, there is a book on impedance spectroscopy by Ross MacDonald, and there are very good review papers written on impedance spectroscopy of dielectric materials. So, I would ask you to go through them and read about the details of impedance spectroscopy, how it could be useful in characterizing dielectric materials. So, we will stop here today. In the next lecture we will talk about dielectric failure breakdown, some failures, and then we will move on to non-lead electric materials. So, thank you very much.